Hello, so in this video, well, if you remember in the last video, we were talking about defining where the ideas behind complex integration actually came from. So in this video, we kind of want to expand on that and kind of show you some of the properties and how to actually take integration of complex numbers, or how to integrate complex numbers. So the first thing I want to do is kind of come up with some definitions. So the idea is it's just a linear operator, and these kind of ideas, these definitions very much follow on from the real case. So yeah, remember we're looking at this, the integration over a curve C of a function of a complex number is going to be equal to, times dz. So the real case, if we have the integration of two functions being added together, so we're integrating two functions being added together, okay, we can just split this integration up into the integration of one function plus the integration of the other function. Okay, so this is what this first one's saying. It's exactly the same in the complex case. Okay, so say for example if we have the integration of a complex function plus another complex function, well that's just the same as we can split up these two complex functions, the integration of first complex function plus the integration of the second complex function. Okay, that's just what we mean by a linear operator. Okay, and then of course we can also have, if we have a constant times a function, we're taking the integration of a constant times a function, we can just take that constant outside the integration. Okay, it's not going to make any difference whatsoever to the integration. We just have that many times the integration. Just because we've got that many times the function, that just means that we can have that many times the integration as well. Okay, that's kind of, it is really simple to see, but it's A-level, so I'm not really going to go into much detail here. It's exactly the same in the complex case. So we have a constant multiplied by a complex function. They can just take that constant out of the front. Okay, the second property that I want to look at is, okay, we're taking the line integral effectively of a complex, a complex number. So let's say we're taking the line integral from this complex number to this complex number. So basically we're finding the area underneath this line. Okay, another way I was taught to do it last year is, if you like, you've got a fence, yeah, and you imagine building a fence along this line. And that's effectively what you're finding. When you find the line integral, that is effectively what you find. You find the area of that fence. Either way you think about it, that's absolutely fine. That might be a slightly more, meaningful way to think about it for you. It's entirely up to you. But basically, we're taking the line integral from this point here to this point here. Okay, and we're going to call that curve C. Yeah. Well, basically, what we can do is actually split this curve up. So we're taking the integration, the curve C this is a complex function. Okay, so we're taking the complex integration. This is theta from Z1 to Z2. Okay, well, we can basically split this curve up. Okay, we can split this curve up, say, from here. We're going to call that part C1 and that part C2. So from here to here, so from here to here is C1, and then from here to here is C2. Okay, well, we can basically do exactly the same thing. It's a bit like adding these two functions together. Okay, because we're adding the function from there to there, so we're basically considering that as one integral, then we're adding to that integral. So it's like, if you like, we're adding two functions together. So this is C1 f of z dz plus integration over C2. That same thing. Yep. Okay, and also if we travel along that curve but in the opposite direction, so now we're doing exactly the same thing. Maybe if I just write it on here. Oops. There we go. So we're doing exactly the same thing along that curve. So instead of going from here to here along that direction, if we do it in the opposite direction now, so let's call this Z0 and this Z1, okay? So we have the integration from Z0 to Z1 of our function with respect to Z. Okay, well that's just, if we now want to do it from the opposite direction, so instead of starting from Z0 and going to Z1, if we want to start at Z1 and go to Z0, we can do that. So we're going to have to we're going from Z1, this is where we're going from, the bottom one's always where we're starting from, to now Z0, okay, of that same thing. It's not exactly the same. It's a bit like vectors, okay? You travel along the vector in one direction, that's what we call the positive direction. But if we travel along it in the opposite direction, we call that the negative direction. It's exactly the same idea here. Because we've defined the direction, going from Z0 to Z1, if we now go from the opposite direction, that's a bit like taking the opposite integration. So we'd have to then use the negative. So basically, if we take the opposite path, then we denote it by the negative. Okay, so how do we actually integrate something? So we've got my integration. Which is over a curve C of f of z dz. So this is my curve C. Okay, start from here, going to here. So this is my curve C. Okay, so I'm going from A to B. All right. Well, remember that I've parameterized this curve. I've defined this curve by parameterization. Okay. So I'm basically saying, as I go along all these, because all of these points on the curve correspond to a complex number. So my complex number, I'll travel through a load of complex numbers over a time t. Okay, so which complex number I'm at will be defined by what time I'm at. Okay, so if I'm at time, say, 3, yeah, I might be here, yeah, so that will correspond to Z3. Yeah, as if I'm at Z5, I may be over here, so that will correspond to Z5. Yeah, hopefully you sort of can see what's going on there. Okay, so in other words, I've parameterized it by that, and the way which you parameterize it, if you remember it, is I always remember it as A plus T times B minus A. I think that was in the first bit of the course actually, how to parameterize complex numbers, but that's fine. Okay, so it's a real part plus, or just if I want to do it this way, it's A plus T lots of B minus A. Okay, except they're now all complex numbers. Okay, and so basically how to do it is, because I'm travelling over it through a time t, I have to include that time t into my integration. Right? So in other words, z is no longer just given as a definite complex number, because I've parameterized the curve. Z is now given by a series of points which are given over a time t. So it's a series of complex numbers which are defined over a time t. So z is no longer just a single complex number, it's actually a series of complex numbers which make up my curve over a time t. Okay, and t goes from A to B. Yeah. So t at times A will be over here, t at time B will be over here, and I've got all the points in between. Okay. So in other words, what I have to do is I have to kind of include that into my integral. So what have I got? Well, I've got my parameterization of my curve, which remember goes from A to B. So from A to B, this is my curve C, going from A to B. Okay, and I've got f of now, well, f is now no longer of z, it's of z of t. Okay, so it's a bit like integration by substitution. Okay, if I let u equal something, so if I now let u equal z, okay, well, I've said that z equals z of t, so if you like, my u is my z of t. U is now my z of t. So z of t is like my u. Okay, and if I now want to, I've basically replaced. Actually, yeah, I'll show you kind of what I mean. So now what I need is I need an expression for dz. I've replaced my u by z of t, so that's my u if you like. If I just replace that with u, maybe I can show you a little bit better. So this is now my u. Well, I now want an expression for u. I can't just leave it as dz by dt. So if I differentiate u with respect to my variable, let's say z, okay, then I end up with something. So let's say that's 1, I don't know. And then basically I can end up with dz equals, something. And, that's kind of the idea behind integration by substitution. So let's just keep this as z of t, okay? And my dz I basically want to replace. Well, dz I can just use by the chain rule, because it's going to be dz. Well, I can define dz as dz by dt. Because if I differentiate this, if I differentiate dz over here, okay, I'm differentiating. What am I differentiating with respect to with t? Because that's my variable on my right-hand side, okay? This is my variable on the right-hand side. That's what z of t literally means. My variable on the right-hand side is t, okay? So dz by dt is kind of how I differentiate z, okay? So, and that's going to be times dt, yeah? Because if I want dz back, then I just can cancel those off, and so therefore that is dz. Just verify that that's dz. Okay, so what I've effectively got is dz by dt times dz. Okay, and that's how I basically integrate complex numbers. It's dz by dt. It's just a chain rule times dt. Okay. If you like, maybe just to kind of try and show you a little bit, what I've effectively got is dz by dt. Okay, well, if I set this up as kind of like I suppose a bit of a stupid way of setting it up, but dz by dt, okay, I've just said the same thing again. Well, basically, I want to make a substitution for dz, right? So this is dt. If I want to make a substitution for dz, right? Well, if I just want dz equals on its own, I take this dt and I multiply it through. Okay, so dz equals dz by dt, so now I can just make a direct substitution. Hopefully that makes that a little bit clearer. Okay, so all those ideas kind of put together. So let's kind of just try and see it as an example, because I think if you can see it as an example, it's going to make a hell of a lot more sense. So basically, what have we got? Our first example is the modulus of z times dz. Okay, well, what is z? Okay, what is the thing which I want to substitute for z? So c is z, which is defined by the modulus of z. So the modulus of z is just going to be 1. Okay, because the modulus of z is just going to be, well, what's it going to be? Remember that z is equal to e to the I theta. Okay, so I'm taking the modulus of that thing. So therefore, that's just going to be 1. Yeah, because the modulus of r is just going to be 1. So, over my curve C, I'm going from 0 to 2 pi. Going from 0 to 2 pi, times my complex number, which is 1. Well, what's now dz? Well, I've let z equal e to the I theta. Okay, that's generally what I do whenever I parameterize something. I'm parameterizing it over a curve. So what's my curve? Well, it's just going to be my circle. Yeah, and my circle is just going to be defined by z equals e to the I theta. Okay, and so now if I do dz by d theta, well, what's that going to be? It's going to be I e to the I theta. Okay, so dz e to the I theta. So dz modulus is just going to be 1. Z is e to the I theta, so therefore dz by d theta is going to be I to the I theta. Why don't I just, why have I just let r equal 1? Well, I'm just parameterizing. So I can let r equal whatever I like, and just for convenience, I just let it equal 1. Because it's parameterization, so I'm just parameterizing it over the curve. Remember, I'm defining the curve. I'm in charge of it. Okay, so I just let r equal 1. Right, so I've got the modulus of z, which is 1. And then I've got dz, which is going to be equal to, well, if I take this, it's a bit like integration. Like I say, it's exactly the same as integration by substitution. Okay, so what does dz by d theta equals I e to the I theta. Then what does dz equal? Well, dz is just going to be equal to I e to the I theta times d theta. Yeah, it's a bit like a fraction. Remember, you can't just strictly treat differentiation, it's dz by d theta as a fraction, but because of the way differentiation works, you can. Yeah, unless you prove it to yourself, you can't just treat it like that. You can't just say, oh, that is a fraction, because strictly speaking, it's not. It represents an idea, but actually, when you look at the idea and the inner workings of that idea, it actually can just be treated as a fraction. Okay, so what does dz equal? It equals this: I e to the I theta d theta. Yep. Okay, so now if I just perform this integration, okay, so I'm just differentiating this with respect to theta. So what have I got? I've got integrate this, so I've got e to the I theta. Yeah? E to the I theta. And I'm going over the full circle. That's why I've said from between 0 and 2 pi, because I'm basically going over the whole circle. This is what I've got. Yeah, this is my z. So all of my z is being defined by e to the I theta, so a circle of radius 1. Yeah? Hopefully I'm trying to make this a little bit clearer. So what is my limit I'm going from? I'm going from here right the way around the circle to here. So I'm doing 0 to 2 pi. Yeah? So my radius is just going to be 1. My radius is just going to be 1. Yeah, my theta going from 0 to 2 pi. Okay, so this is what I end up with. So let's just evaluate this. It's going to be e to the I, so I'm just replacing theta with 2 pi, minus e to the I 0, e to the 0. So that's just going to be e to the 2 pi I. Let's just rewrite the I 2 pi as a little bit neater, minus 1. Okay, so there we go. So that's quite nice. That's a nice one, if you like. Okay, so now let's look at this one. Let's look at this example. A little bit more tricky. What's going on? A little bit more tricky. So we've got the integration over a curve C of the real part of z. The real part of z with respect to z. Okay. Well, again, we just parameterize our curve or our z over a circle, e to the I theta, going from 0 to 2 pi. Okay, going from 0 to 2 pi. Okay, so again, dz by d theta. dz by d theta equals I e to the I theta, which implies that dz is equal to I e to the I theta times dz. Okay, so what's the real part of z? Well, I'm now going to rewrite this thing. I'm going to rewrite the thing which I parameterized. Put that up there. There we go. I'm going to rewrite the thing which I'm parameterized in trigonometric notation. Okay, so it's just going to be cos theta plus I sine theta. Okay, so what's the real part of z now? It's just going to be the cos theta bit. Okay, so this is the integration from 0 to 2 pi of cos theta. So basically, I want to get rid of my dependence on z. I want to just replace it with thetas. Okay, so my real part, I can't see my real part from e to the I theta form, so I then have to kind of put it in trigonometric form, so then I can separate it up into a function of the real part plus I times plus the function of the imaginary part. Okay, so I'm just taking the real part of this function, which is the cos theta, times by my dz. Well, I've made the substitution for dz as I e to the I theta dz. All right. Okay. Now there's a couple of ways. Sorry, that's not dz. That's d theta. There's a couple of ways that I can kind of look at this. The way which I would be tempted to do it is integration by parts. Okay, but it will take kind of a little bit of time to fall out. The way which you can do it is make a substitution for cos theta. Make a substitution for cos theta, and that's using hyperbolic functions. Okay, so remember that cos theta is equal to e to the I theta plus e to the minus I theta over 2. Okay, so if I now just replace that in there, I end up with 0 to 2 pi of, I'm sticking the half out the front of the brackets, e to the I theta plus e to the minus I theta. Okay, and that's all still multiplied by I times by d theta. And actually, because I is just a constant, I'm going to stick the I out the front as well. So we've got I e to the I theta there times d theta. Okay. So now I just kind of look at this. So I've got, now what have I got? I've got I over 2, 0 to 2 pi. Hopefully this is quite a nice way of doing it, because then hopefully the exponents cancel out. So I've got e to the I theta times e to the I theta. So this is effectively e to the I theta squared, so e to the I 2 theta. Okay. Plus, this is e to the I theta minus I theta times e to the I theta. So I can just add these powers together. Well, obviously they're going to cancel, they're going to go to 0. Okay, so I've got e to the 0, which is just 1. Okay, it says 1, okay, and that's times d theta. Okay, still got I over 2, a little bit more work to do. So now I can just integrate this directly. Okay, this is from 0 to 2 pi. So I'll do it directly now. 2 pi, so let's integrate this. So what have I end up with? I end up with, well, it's going to be the same thing over the derivative of this thing. So the derivative of this thing will be what? It'll be 2I theta differentiated, which is going to be 2I. So it's all going to be over 2I. Okay, that's just integration by recognition. So I'm just looking at this power, and I know that basically what I'm after is this thing differentiated. This is what I'm going to have to divide by. Okay, because it's e, right? So yep, and then plus theta. Okay, let's just evaluate this now. Got I over 2 e to the 4 pi I over 2I, yeah, plus 2 pi, and then this is just going to be 1, so it's going to be minus, I'm just putting 0 in, so I've got e to the 0, which is going to be 1 over 2I, okay, plus 0, so that's fine. And let's just do a little bit of tidying up, so let's cancel the i's off here, so I end up with e to the 4 pi I over 4 plus 2 pi I over 2 minus, what's this going to be, 1 over 4. Okay, so there we go. And can I simplify that down any more? I'm not sure. Or maybe there's 2's there. Look, cancel those 2's off. Not or maybe, yeah, actually, let's put these two fractions together. So end up with e to the 4 pi I minus 1 over 4 plus pi I. Yeah, okay, that's pretty much as simple as we can get it. Okay, now let's consider the last one. This is kind of the last one in this series of videos. So we've got C, and we've got 1 over Z with respect to Z. Okay, we've got exactly the same thing going on. So we've got, remember, Z is equal to I e to the I, sorry, not I e to the I theta, e to the I theta. And then when we differentiate Z with respect to theta, we end up with I e to the I theta. And so that implies we just want dz for the substitution is going to be I e to the I theta times d theta. Okay, so we've got that going on. So we just make our substitutions now. So we're going from 0 to 2 pi, because that's what theta is defined as. 0 to 2 pi. If you did vector calculus last year, this is sort of exactly the same idea. It's just with complex numbers. Okay, so you're used to parameterizing and introducing new variables. So this is 1 over e to the I theta, and this is I e to the I theta d theta. Okay, cool. I theta d theta. It's I e to the I theta. Okay, so let's try and sort of do this out. So hopefully you can see that the e to the I theta is cancelled in both cases. So we just end up with 2 pi I d theta. Yeah, that I to the I theta cancel. And so that's quite a nice easy integration. So we end up with the I theta over 0 to 2 pi. So that's equal to 2 pi I minus 0. So it's just going to be equal to 2 pi I. 2 pi I. So basically, how do you do it? How do you integrate it? Basically, you have to kind of make a substitution because you're parameterizing over a curve. And what's that parameterization you always make? We always make it over a curve, and we always just make that curve a circle. Okay, we're basically parameterizing over our circle, and we always make that circle radius 1 just for convenience. Okay, you can make it other numbers. It just be bigger or smaller. But to be honest with you, for convenience, just make it 1. You know, less numbers involved. Let's just make it 1. So Z is equal to e to the I theta. Okay, so when we basically make a substitution, we need to differentiate dz by d theta, which is going to be I e to the I theta. Okay, then that implies that our direct substitution, so we want to replace dz, that's going to be I e to the I theta times dz. Okay, so hopefully that makes a bit of sense.